Hello everyone. Last time we met, we were talking about how we could view multiplication of either large numbers or sometimes even what we refer to as binomials as being this kind of cross interaction that occurs whenever you break something down to its smaller parts. And really what we're trying to capture with that image of drawing out this grid and looking how different parts interact through multiplication with other different parts is we're trying to put a picture behind this idea of distribution. When you talk about having, let's say, 35 times 24, you can look at 35 as 30 and 5, 24 as 20 and 4. You can do the multiplication in parts and then combine all those parts at the end, because it makes sense that if you're talking about combining piles and groups, it doesn't really matter which of the piles and groups you form first, so long as they're all accounted for afterwards. We're going to use the exact same idea to help us kind of expand and to come up with this concept that a lot of people hear called foiling. Foiling isn't a proper math word. It's something that the math community at large has kind of started to give a life of its own, but really we're going to see that it comes from no other roots than the idea of distribution. And once we finally anchor down and get comfortable with this idea of multiplication, we're then going to go into division, because in mathematics we're always interested in not just how do we run problems forward, but if we wanted to, how could we do the exact same process in reverse. So let's go ahead and jump right into completing our notes for this section. If we keep track, back in the earlier question of everything that's being affected, and we draw our kind of square, now that we know our little grid, I guess, is a nice organization for all of this idea. I'm going to have in the first box the effects of the first two terms, my x times my x in this case. So this would be, right, for x plus 4 and x minus 4. I'll put the negative 4 there, so we always have x plus negative 4. That'll help me organize my thoughts. So in the first box, it's always going to be the first two terms that affect each other. In the next box, this one maybe we look at down here, it's going to be these two that are affecting each other. In this box here, it's going to be these two that are affecting each other. And lastly, we're going to have this box, which is these two affecting each other. The acronym that many of you have heard is of FOIL stands for first, outer, inner, and last. And it's just a way for us to recall that there are 4 steps whenever we multiply this binomial times another binomial. And it's that the first two terms are going to multiply, the outer terms are going to multiply, the inner terms are going to multiply, and the last terms are going to multiply. And if you're comfortable with where this comes from, you have my permission to use this as a shortcut. It can be quite helpful. So let's see if we can't do everything that we have in this problem lickety-split. X times x is x squared. X times the negative 4, the outer terms, gets me negative 4x. 4 times x gets me positive 4x. And 4 times negative 4 gets me negative 16. I can then simplify all of this by recognizing that the first two terms are exact opposites of each other, and so they'll cancel out and leave me with x squared minus 16. That's pretty cool that we can do that so quickly. Also keep in mind that this is a very interesting statement that we had talked about before. This is what we call the difference of two squares. Notice that x squared is a square made from x, and 16 is a square made from the number 4. So every once in a while when you're playing around with these, if you keep track of the context, you find out something pretty interesting. What this says is that if you give me any square at all, that you started with some kind of integer number, or actually not even, if you just give me any square at all, and then you take 16 away from it, that is going to leave me with all the tools I need to make a rectangle that is x plus 4 wide by x minus 4 long. Let's look at a quick example of that one. If I said, give me the square made out from 10, that would be 100, and then take 16 away from that. That leaves you with 84. And I can tell you without doing any math, any thought in my head, just because I understand this structure right here, that's going to be a rectangle. I can organize 84 into a rectangle that is 10 minus 4 wide and 10 plus 4 long. In other words, my rectangle is going to be a 6 by 14 rectangle. Kind of cool when we take a little bit of time to recognize these properties, these inherent truths that have to occur due to us just playing around with some symbols on the paper. Okay, the last thing we're going to do with multiplication is we're going to hit on what we can do with these third power or higher power binomials. So what this essentially is the exact same idea we're working with before, but there's going to be a little bit more, actually quite a bit more, that we're going to have to organize. And after we go through this, I'm going to show you that, again, if we're paying attention while we're doing our work, we can pull out a shortcut that helps us to do problems like this much, much quicker. But it's going to require you to pay quite a bit of attention and to keep track of everything in your head. So don't just be copying by, but make sure that if you need to add some notes onto your paper, do that as we're talking. Okay, let's see what we can do. If I was asked to find the product of 5 minus 3z to the third power. Well, we got a little bit of a hint here. It is a product, and that product is because I have an exponent. Exponent means multiply something by itself a certain number of times. So I always find it helpful whenever I see an intimidating problem to write this into a slightly more familiar format. So let's really just take some time. We'll become comfortable with our own humility here, and we'll just write this out in about the most comfortable way that we could given the circumstances. We're multiplying something by itself 3 times. Great. What I recognize now is that I have a thing being multiplied by other things that have addition and subtraction. That means that my distribution rule applies. Take a look at how I see that. If I make all of this my yellow highlighting, and I say that this is all one thing, one number, it would result in a number, and that number is going to be multiplied by 5 and then multiplied by a negative 3z, that tells me that I can use my distribution property. Let's see how that would happen. Okay, so we're going to do this whole yellow highlighting times 5 first. That gets me 5 times 5 minus 3z times 5 minus 3z. Okay, now I'm going to do this entire yellow highlighting times the negative 3z. That'd be negative 3z times the yellow highlighting, 5 minus 3z, and 5 minus 3z. Excellent. Now let's see if we couldn't do that exact same idea again. Notice that now I could recognize I have yellow highlighting here. That's going to be multiplying by 5 minus 3z, and over here I have yellow highlighting. That's going to be multiplied by 5 minus 3z. In fact, in order to help keep track of all of this negative on the right-hand side, I might choose to think of this instead as a plus a negative 3z. You can always do that if you see a subtraction symbol, and that's going to help to remind me that I'm going to be taking this negative 3z and multiplying that through, not just the number 3 and the variable z. Okay, enough talk. Let's see if we can't distribute this on through. We're going to do 5 times 5 minus 3z, that's my yellow highlight, and I'm going to be multiplying that by another number 5. And then I'm going to, let's see, multiply 5 times 5 minus 3z, and I'm going to be multiplying that by a negative 3z. All right, not too bad. That was the first part. Let's do the next part. So let's do plus, because I'm going to use plus, and then I'm going to bring my whole negative amounts over, so it'll be plus my negative 3z, 5 minus 3z, times 5. And then I have plus my negative 3z, times my 5 minus 3z, times a negative 3z. Excellent. Just to kind of clarify where everything happened here, notice that the yellow highlighting is here, 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 and here. The yellow highlights that I distributed to the binomial, to the 2 named terms that I had in the last little parentheses. So just to kind of clarify that one, here's kind of your 5, and it went down here. Your negative 3z went right here. Your 5 went right here. And your negative 3z went right here. Okay, so we've almost got it so that we only have multiplication that's occurring within all of these parentheses, and then the addition's kind of enforced to the outside. Let's try doing it one more time, because we have the ability to do that once more here. where now I have a 5 being multiplied in. Maybe that's a little bit odd. Let's see if we can't reorganize that. So I'm going to rewrite the exact same thing. I'm not doing anything different here. I just have 5 times 5 from here and here multiplied by 5 minus 3z. We'll just take a moment and kind of organize our thoughts. So then I have plus 5 and negative 3z times 5 minus 3z. That's from this and this being moved to the front, multiplied by here. Then I have plus 5 negative 3z times 5 minus 3z. That's from moving this 5 to the front over here, which I'm allowed to do. Again, commutative property, just reorganizing my multiplication. And then the last thing is that I have a negative 3z, and then 5 minus 3z. All right, one last step of distribution to go. And then we're going to see a really interesting truth that kind of pops out and makes problems like this be so much easier in the future. Okay, what are we going to be distributing here? Let me use a green highlighting. So I'm taking this 5 times 5. I'm going to be affecting the 5 and the negative 3z. I'm also be taking this 5 minus 3z, affecting everything in its addition and subtraction. So let's start to write that out. 5 times 5 times 5 would be the first term. Then I would have 5 times 5 times negative 3z would be the second term. So that'd be 5 times 5 times negative 3z. Again, your parentheses are going to be very, very helpful. Then I have this one that I'm working on. That would be 5 times negative 3z times 5. And then I have 5 times negative 3z times negative 3z. So that'd be 5 times negative 3z times negative 3z. Excellent. Okay, so we've gotten through the first two. Let's keep going. We've now got some green highlighting here. I'm going to be multiplying that to some addition and subtraction. So that would be plus 5 times negative 3z times 5 for the first part. I'm going to need to go on the next line, plus 5 times negative 3z times negative 3z for the second part. Okay, great. Now the very last one is going to be multiplying in this number time addition and subtraction. Okay, so that would be negative 3z times negative 3z times 5, and then I have negative 3z times negative 3z times negative 3z. Oh golly, so much to keep track of there. But here's the really interesting thing. I'm going to write this in a certain way, and it's going to help to reveal that all of this work that we did actually came about from a pretty, I don't know, kind of predictable process, if you will. Notice that the very first number is 5 times 5 times 5, and that's going to make sense that I have 5 times 5 times 5. I have 3 of those because I had an exponent of 3. So I'm going to rewrite this as 5 cubed. On the next one, I'm going to write this as 5 squared times negative 3z. On the next one, I'm going to write this as 5 squared times negative 3z. Oh, so actually I have 2 of them. Let me combine that. I have 5 times 5 times negative 3z and 5 times 5 times negative 3z. That's just 2 of these 5 squared negative 3z's. Maybe I'll save that for my next line of work. I'll write it all out and then we'll simplify it. Okay, so I have that. Let's do the next one. That'd be 5 squared times negative 3z squared plus 5, oh, another one, squared times negative 3z squared. It's almost like I had some kind of rippling effect where I crossed over as I was doing all of this math. That's kind of interesting. All right, plus 5 times negative 3z squared plus 5 times negative 3z squared. It's happening still. And then the very last one, I have negative 3z and 3 of those. So we'll say to the third power. Hey everyone, we had some production issues, so I'm going to record this over what we were just talking through. So we've got to this point where we've expanded this problem as just about as far as we can go, and now we're getting ready to fully simplify everything. But we start to notice that there's this overlap pattern that behaves regardless of the numbers that we started with. We've got some negative 3z times 5 times 5, some negative 3z times 5 times 5, a third one of those occurrences, and then we have another 3 occurrences that occur from the negative 3z times negative 3z times 5, and that repeats itself 3 times. So you've got 8 terms in total, and you can almost categorize those and think about them as the very first of these terms is going to be what happens when the 5 gets multiplied by itself. So we're always going to have that first term being cubed. But we have 8 total terms by the time that we do all this expansion, because we went from 2 to 4 and then we went from 4 to 8. So that would be leaving us with 3 repeats where the negative 3z occurs once and the 5 occurs twice. And then we're going to have 3 more of those that are from when the negative 3z occurs twice and the 5 occurs once. And then lastly, we're going to have the instance where negative 3z just gets multiplied by itself 3 times. And you could feel free to go ahead and simplify all this out. We'll do this, I guess, real quick for the numbers. 5 times itself 3 times would be 125. We would then have 3 instances of this negative 3z times 5 squared. So that would be 5 squared is 25 times 3 is 75, and then 75 times negative 3 would be negative 225z, so that would be negative 225z. The next one would be 5 times 3 is 15, times negative 3 would be negative 45, times a negative 3 again would get us, what, 135, so we'd have 135 z squared. Oh, and there should have been a z for this other term. And then the very last one is just going to be negative 27 z cubed. That's what happens when you multiply negative 3 by itself 3 times. But much more importantly than 27 z cubed, there we go. Much more importantly than getting a specific problem right is figuring out how we could do a general problem in the future. Notice that we can now jump ahead for all numbers in the future and just simply say that whenever I have a number in the front and I have another number that I'm eventually going to have where I repeat 3 times, and then I have 3 overlaps that occur where one side occurs more often than the other, so that would be 3 5s and negative 3z squares. I'll have 3 5 squares times the negative 3z, and I'll have negative 3z times itself 3 times. We'll now take a moment and see if we can generalize this using other letters. So let's try, what if I didn't have numbers at all? What if I just had variables? What if I had something like a plus b, and I was trying to cube that so I could talk about any numbers in any terms? Super simple. I know that's going to be a cubed plus 3 ab squared plus 3 a squared b plus b cubed. Kind of cool. And now we also know that even if I was to write something like a subtraction here, a minus b cubed could be thought of as a plus negative b. So I can ripple everything through the exact same way that I had just worked on. A cubed plus 3 times a times negative b squared. I'm just grouping the ideas, those entities that are in my original parenthesis, and then I have 3 times a squared times negative b plus negative b cubed, which all in all gets you a cubed plus 3ab. That's made positive because you've got a squaring of that negative, and then you've got a minus, oh, there we go, put that back, that was a, okay. So we have our next one, which is a minus 3a squared b, and then minus b cubed. So you've now created these special equations, these special formulas for any time you have something plus or minus something else raised to the third power. In other words, whenever you have a binomial that's being cubed, you can jump right to these equations because we spent all the time modeling out that logic. So that's a lot of things to kind of process and to work through. I want to take a moment and we're going to step away from manipulating those symbols and moving the variables around. And I want to show you the last little bit of this section, which is on division. But similar to how we just tackled all of those difficult problems from the last part of this section, I want to give you a different perspective for how to view division that helps to kind of remember what it is, so that we avoid this idea of just simply doing rules, and we can instead be taking a look at the meaning that's happening behind the manipulation. Now, I'm going to introduce you to this idea of a 5-to-1 machine. And so a 5-to-1 machine essentially just means that in this machine, if I put 5 dots here, then I'm allowed to collapse all of those dots, take them away, and put another dot in the 5 box. So if I have 5 ones, I can take all those out and I can put 1 dot in the 5 box. If I have 5 dots in the 5 box, I can take all of those out and I can replace it with 1 dot in the 25 box. Okay, does that make kind of sense? It's almost like we're collapsing, and then similarly I could go backwards as well. If I wanted to take one of these dots away in the 25 box, I'd have to put 5 dots in the 5 box. Okay? Let me show you why this is a little interesting. If I was to look at what this machine was currently trying to show me, it looks like I have 2 dots that are in the 25 box, I have 1 dot that's in the 5, and 3 dots that are in the 1. And we're just playing around with an example here, but what would that be? Well, 2 of these 25s would be 50. I'd have 1 dot in this 5, that would be a 5, and then I would have 3 dots in the 1, that would be 3. So in total, this machine is currently displaying 58, the number 58. It's just doing it in a way that's what we might call a base 5. It's using groups of 5 to kind of move throughout this machine. But in our traditional number, we would say this is 58. So the machine reads this as 213. We read it as 58. Kind of interesting. And actually, this is exactly how machines like computers behave all the time. They read off in binary. They read in ones and zeros. So they sometimes have numbers that are like something like this. What they interpret that as is something that's not 101,101. They read it as a number that's actually something that's much smaller and that we're familiar with. So even though they're kind of communicating through these machines, the numbers that they mean, we're used to seeing them laid out like this. Kind of a fun little bit of trivia. Let me show you why I'm kind of stressing this. If you become comfortable with the idea of counting in different numbers, you can actually recognize that different cultures around the world as humans were developing actually counted differently than each other. We're used to counting on 10 fingers and 10 toes, right? But we only count up to 10 and then we go to 11 and 12, etc. So we're used to 10 different numbers, 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. We're used to 10 of these numbers that correspond with our fingers because that's how we counted. But that's not entirely true. There are some cultures that actually counted on their knuckles, and I might have shown you this before, but they count on their knuckles by using their thumb to indicate it. So they go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. And then they would hold up a finger on the other hand to say I have one group of 12. And then they could do that again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And they would hold up a second finger, so they now have 2 groups of these 12s. Okay, well, why is that something that we're only hearing about now? Well, for example, if I said, what would it be if I gave this as my indicator? We could represent this using a machine. In fact, this would be a 12-1 machine, where on one hand I have 1, 2, 3, 4, 5. I was holding up the number 5, and on the other I had 2 groups of this 12. Let's see how we could kind of understand how other cultures talk and count by using this 12-1 machine. So on our 12-1 machine, we have 1, we have 12, and then that'd be 12, that'd be 140. And what I was holding up was 1, 2, 3, 4, 5. I was holding up 5 on my single unit, so we could put 5 little dots in here. 1, 2, 3, 4, 5. And I was holding up 2 fingers for the groups of 12 that'd be 2 here. How much would that have been? Well, that'd be 2 12s, which is 24, and then that'd be 5 singles, which would be 5. So I was holding up 29. I was counting in a way that was common back in Middle East and India, back at the 600 ADs just about, and is in fact the reason why we have 60 seconds in a minute and 60 minutes in an hour. You might not have known that. You have 60 seconds in a minute because in Middle East and India, the study of time and the study of direction was being championed. And they were counting in such a way that after they counted to 12 and then held up 5 fingers, they had 5 groups of 12, which is 60. This is also why, if you actually have ever flown a plane or you talk with somebody who's in navigation, they will use portions of degrees, portions of travel that they measure out in 60ths. Kind of interesting. So ours is not the only way of counting, and when you recognize that there's different ways that we can represent them in these machines, it makes breaking things apart a little bit more interesting. So we were talking about binary before. Let's see if we can figure out what this number would be in binary. Binary is where computers only count 1, and then when they try to count a second one, they can explode that and put it in the next box, so they count in groups of 2. So let's see real quick. We can do this in a machine, a 2-1 machine. So our very first one would be 1, and then I would be able to explode 2 of those to get into the next box. So I guess the next box would be representing 2 groups of 2, and then I could explode 2 groups of 2 to get to the next one. I guess that would be 4, and then I could explode 2 groups of 4 to get 8, and then I would have 16, and I would have 32. Let's see if we need all of them or not. Okay, let's now put our number in there. We have 0 in our 1 box, so I'm not going to put any dots. I then have 1 dot that's going in my 2 box. Okay, good. And then 1 dot that goes in the 4 box. I then have nothing that goes in my 8, and I have 1 that goes in the 16. So just to clarify, the 1s went here, the 0, 1, 1, and 0. Let's see what a computer would think that this number actually means. Well, there would be no groups of 1, so I'll do 0 groups of 1. I would have 1 group of 2. I would have 1 group of 4. I would have 0 groups of 8. I would have 1 group of 16. That would get me 0, 2, 4, 0, and 16. That's the values that the computer thinks we here. And when you combine all that together, you're going to see we have 2 plus 4 is 6, plus 16 is 22. So a computer thinks that this number that we would normally read as 10,110, when it sees 10,110, it's thinking 22. Very interesting. It's almost like translating between different languages, but this perspective is helpful because if I can convince you that there are different machines in different places in the world where people count differently, it makes sense why we might not want to be talking about doing division with numbers anymore, but instead be talking about how do we do division with variables, these placeholders that really could take any number. And I'll show you what I mean. Let's take a look at how we would do division with some of these different numbers. 402, and let's say I'm dividing it into 3. So I'm going to make my 10-1 machine, because when I read 402, where we're talking back about how humans are kind of communicating nowadays, so in our base 10 system, so we have 402, that means that I have a place, my 1's value, I have a 10's value, and I have a 100's value. So I can go ahead and explain it like this. I've got 402, so it's 4 hundreds, 4 dots in my 100. I have nothing in my 10's, and I have 2 dots in my 1. And I want to divide this into groups of 3. Well, no problem. I can see that there's a group of 3 right here, quite visually. So that's 1 group of 3. That's great. I can't really see another group of 3. But remember, this is a 10-1 machine. I can explode and unexplode these dots so long as I keep this meaning. So I'm going to explode this way. We're going to take this dot away, and instead I'm going to put 10, 3, 4, 5, 6, 7, 8, 9, and 10. I'm going to put 10 dots back over here in the 10 space. And I'll erase it to make sure that I don't have any confusion on that. Okay, good. So now I've got still my group, and I'm looking for groups of 3 because I'm dividing into 3. Okay, well, here's a group of 3. Here's a group of 3. Here's a group of 3. And I have 1 left. So let's explode it. Go ahead and explode it in the other category. So So 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And look for groups of 3. So my groups of 3 again would be, I'll use green this time. I have a group of 3 right here. I have a group of 3 right here. I have a group of 3 right here. And I have a group of 3 right here. Perfect. So what that tells me is that I have one group in my hundreds. I have 3 groups in my tens. And I have 1, 2, 3, I have 4 groups in my single place. And you can actually verify with your calculator if you'd like that 402 divided by 3 is equal to 134, because that's what it means. It means that out of my hundreds, I was able to give everybody 100 before jumping over to giving them some 10 and giving them some 1s. If this feels odd, perhaps you've seen division instead done like this, is what we would call long division. 3 divided by 402. Notice how you did it in long division is the same way we just did in the exploding dots. I just gave you a picture to help you recognize it. We'd normally say, how many times does 3 go into 4? And you'd say it goes in 1 time. So 1 times 3 would be 3. You would then subtract, and that would get you down to 1, and you'd bring down the 0. Notice I have 10 over here, almost like when I exploded right here. But I'm looking for how many times does 3 go into 10? That would be it goes in 3 times, because 3 times 3 would then be 9, and I could subtract, and that would get me 1 and bring down the 2. So it's almost like I have 12 dots in the singles category I still have to break up, like I did over here. So we'd say, how many times does 3 go into 12? And we'd say it goes in 4 times, so 3 would be 12. I have nothing left over, no remainder. Perfect. Okay, so let's go ahead and do a couple more of these examples. When you're working with really large numbers or negative numbers, we can represent that using a similar picture. So let's see what we can do for this monstrous one here. We're going to need lots of boxes in our machine. So we're going to have negatives, so maybe I'll use open circles this time. So I've got 6 open circles, 1, 2, 3, 4, 5, 6, that are going to appear in the last box. I've got nothing in the next box. I've got 5 in the next one, 1, 2, 3, 4, and 5. Then I've got 4, 1, 2, 3, and 4, and then I've got 1, and then I've got 2. So this would be in my 1s, in my 10, in my 10 groups of 10, that'd be my 10 square category or my 100 category. And then I have my 10 cube category, that'd be my 1000 category. I have my 10 to the 4th category, that'd be my 10,000 category, and then I have my 100,000 category, so right here. All right, let's go through and let's find some of these groupings. So now I'm looking for groupings of 102. So 102 would be, I'm looking for dominoes essentially that are 1, the opposite, and then 2. So I'm using open circles this time to show that I have kind of like a negative group, an opposite group. So let's go through and see what I can find. I've got 1 here that could partner up with those 2. I've got another one that could partner up with those 2. So that gives me 2 groups that are in this category. I'll kind of put 2 little tick marks here. Then what else can I find? I can do 1 here with 2. I can do, which would give me a group in the hundreds category, a group in the hundreds category of 102. And then I would be able to go through and say, maybe I'll use green. I've got 1 here and 2, 1 here and 2, and then 1 here and 2. Gives me a total of 3 groups in the ones category. So all in all, I can say I have 2 groups in the thousands. So I have 2,000, 100, no 10s, and then 3 groups in the 1. So I guess I should reorganize my parenthesis there, or my comma there. So that'd be 2,103 opposite groups. We'll call that a negative. Now, why is it that some teachers will teach more with the long division style than the others? Because it's faster, it doesn't take up very much room. Some people are more familiar with it and it's traditional. But why do I teach the dots and method, the exploding dots method, the negative dots method? Because I think it's a little bit more fun. I think it gives us a nice picture to talk about why things are behaving the way that they are. And not to mention it captures the same idea and has that little bit of cool factor of like, oh, that's what we've been doing this whole time. Kind of fun. Now, the reason why I started to refer to things a little bit more as like that 10 and then 10 squared for 100 is because if we think about these machines as taking groups and then groups of groups, that's really what these exponents are, is that a 10 to 1 machine has the first category being 1 and then a group of 10 of those, and then a group of 10 of those 10s, etc. A 2-1 machine starts with 1, and then I get a group of 2, and then I have 2 groups of 2 would be 4, and then 2 groups of 2 would be 2 cubed. And you can think of this however you want. We start with 1, maybe 12. That's where the 144 came from, was 12 squared. So when you start to talk about these in a general behavior, we don't need to talk about number to 1 machines. We can talk about them as x to 1 machines, and we can still do the exact same division we would want to. So let's suppose that we are trying to divide, and you might see this question written as 2x squared minus 7x plus 4 divided by x plus 8. We'll use parentheses to group it all in. How would we do this? The exact same way. We could organize it in an x to 1 machine. So we could say that we have our 1, we have our x's, and then we have our x groups of x. So that'd be our x squared. Then we have 2 of these x squared, so we'll put 2 of them. I have 7 opposites of x, we'll put in 7 of these circles, 4, 5, 6, and 7. And then I have 4 in my ones category. And I'm trying to find groups of x and 8. That would be 1x and 8. 3, 4, 5, 6, 7, and 8. So now let's go through and see how we would do that division using our x to 1 machine. Well, the first thing I would want to do is probably try to group one of these x squares with something that's in the x category, but I don't have any of them there. But in math, if we ever want to create something, we can, so long as we balance it out. So let's just put the 8 dots that I would want to be partnering it with, 3, 4, 5, 6, 7, 8, and I'll just balance it out with 8 more of these open circles, these anti-dots, 1, 2, 3, 4, 5, 6, 7, and 8. That would allow me to get my group. So I would be able to group all of that together and say that's one group. Perfect. I could then do that again with this dot. I would just need to add in 8 more of these dots and 8 more of these anti-dots. And then I would need to do the same thing with the anti-dots, but I would need to be putting in some more of these anti-dots over here and then balancing them out with closed circles. So we can see the idea behind it, but maybe it's better that we switch over to the symbology now to help organize our thoughts a little bit better. So let's use the notation the same way that we were used to using long division. Let's do 2x squared minus 7x plus 4, and let's divide that by x plus 8. Well, as we said, how many of these groups could I get of my x plus 8? Well, I could say that just similar to how we do long division, if I put 2x here, 2x times x gets me 2x squared. And that's almost like, in fact, it's exactly like the 2 groups I would have gotten when I was trying to divide out that 2x's or the 2 in the x squared part of my machine. So that multiplies on through. I got 2x times x gets me 2x squared, and 2x times 8 gets me 16 x's. Almost like how I would have needed to introduce 8 and then 8 more of these x dots in order to balance this all out. Okay, so when I take all those away, what am I left with? I'm left with no more x squares, and I'm left with 23 x's. 7 from my original anti-dots, and then another group of 8 and another group of 8 to balance out all of that workings, and we bring down the 4. So then we say, okay, how do I take something and multiply it by 8 to get me my 23? Well, we'd say I could multiply it by, let's see, by about 23 of them, because I would be able to find 23 pairings in this picture here if I was to say, let's take each of these anti-dots and try to create a little bit more of these anti-dots in the next category over. So we'd say, okay, how many would that be? That'd be 23 of them. I'd put 23 times x gets me 23x. 23 times 8 gets me, that'd be 160, and then 24, so 184. 184. And trying to balance all of that, I would have a number of anti-dots that would be created, and that would leave me with negative 180. So in all, when I finish all of this up, I would have 2 groups that I was able to have in the X category, 23 groups that were in the individual category, and then I would have a remainder of 180 that I wasn't able to divide yet. So I would have negative 180 that still needed to be divided by x plus 8. So as you can tell, if we take a little bit of time to develop our understanding for what it is that we're doing behind the symbology, we're able to get to a number of shortcuts and some cool representations that help us out with doing some problems like this. We're able to take divisors, a little bit of a vocabulary word there for you, divisors like this x plus 8, and then dividends, what we're starting with, and we can do the division even if I don't know what x is. Even if I don't know what my machine is, I can still talk about grouping things out in a similar fashion.